number and operations, particularly fractions, for the 4th grade this week. Just like with 3rd grade, I wanted to make sure that fractions had their own separate week. Students are uncomfortable with fractions, as I stated before, so the more time that we can spend developing fractions, the better off we are. And here is a list. Look at all of these 7 different particular standards that we need to cover in 4th grade. Again, why it has its own week. There's so many things that we need to talk about. So let's talk about first comparing two fractions using less than, greater than, or equal to. We can compare and order fractions if we have unlike numerators and denominators. So to do so, I'm going to use an area method. Notice that my boxes are the same size, however, one is split into thirds and one is split into eighths. So I'll want to shade 2 copies of 1/3 and 3 copies of 1/8. So 2 copies of 1/3 would be 2 of the 3, and then 3 copies of 1/8 would be 3 of the 8. I can see that 2/3 is more shaded than 3/8, so therefore 2/3 is greater than 3/8. Let's compare 4/5 and 8/10, again using an area model. So on the left, although the unit is the exact same size, they're split into different sizes. So on the left we have fifths, and on the right we have tenths. I need to shade in 4 copies of 1/5 and 8 copies of 1/10, which looks like this. I can see then that the exact same amount is shaded. So therefore 4/5 equals 8/10. We can also use a number line to compare. So on my top line, we already know that 4/5 equals 8/10. So I have a double number line. I split the top line into fifths and the bottom line into tenths. So there are 1/5, 2/5, 3/5, 4/5, 5/5, which we know is the same as 1, and 1/10, 2/10, 3/10, etc., all the way through. I have 4/5 and 8/10 labeled, so I have 4 copies of 1/5 and 8 copies of 1/10 listed here. And I see that they are the exact same location on the number line. So therefore they are equal to each other, just in a different way. Let's order the following fractions from greatest to least using number lines. I've got 3 different number lines. Each number line will represent one of our fractions. I see on the top that I'm split into 12ths. The middle is split into 6ths, and the bottom is split into 8ths. So when I look at 1/12, 2 copies of 1/12, 3 copies of 1/12, etc., I see where 9/12 is located by counting on my number line. I can do the same with my 6th line. So each one represents 1/6 or 1 copy of 1/6. So I need to go where 2 copies of 1/6 is located, and I see it's listed there. And finally, 4/8. So 1/8, 2 copies of 1/8, 3 copies of 1/8, and 4 copies of 1/8. So when I want to label them from greatest to least, I see that the furthest distance is 9/12. The second one would be 4/8, and the third one would be 2/6. So 9/12 is greater than 4/8, which is greater than 2/6. When we compare and order fractions, we think about whether the numbers are less than, greater than, or equal to each other. This is true when working with whole numbers and with fractions. Remember that fractions are just a number on the number line and should be treated just as such. We can recognize and generate equivalent fractions, as you probably noticed with that last problem. We didn't have to write 2/6. There was another way we could represent 2/6. So to do so, we'll practice by combining and partitioning fractional pieces on a model and a number line. So what fraction does this model represent? I see that there are 6 pieces, so each piece represents 1/6, and I see that there are 4 copies of 1/6 shaded, so therefore it equals 4/6. Now cut each piece into 3 equal parts. What is the new fraction represented? So I took each sixth and I cut it into thirds. So now I see that there are 6, 12, 18 pieces. Well, of the 18 then, there are 1, 2, 3, 4, 5, 6, 12 copies of 1/18 shaded. What fraction does the point represent on the number line? I see that we are split into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces. So there are 1/10, 2/10, 3/10, 4/10. Combine every two segments together. What is the new fraction that is represented at this point? So notice when I look at these two here, I combined and reduced them into one. So I kind of brought it over and dropped it down. So now we're only 1, 2, 3, 4, 5 different segments. So each notch represents 1/5. Therefore, there are 2/5 shaded, or 2/5 whereas the dot is. The number line is certainly underutilized in elementary school, however, is extremely effective for modeling for students. There are many things that we can do with the number line, such as partition and iterating to generate fractions. The roles of number as a multiplier and denominator as a divisor are certainly made clear. The process of fractional parts decreasing in size while the copies of the unit fraction increase in number. There is a clear differentiation between the fraction measure of 2/3, the length of the line segment from 0 to 2/3, and the rational number 2/3 used as a unique point on the line. The ability to partition to represent increasingly more precise measures is boundless. Creating equivalent fractions for any given fraction, be it less than or greater than 1, is easier through the use of the double number line. Not to mention how visual the number lines can be. Have you ever used the multiplication table to create equivalent fractions? So here I have the multiplication tables 1 through 12. Let's say we have 3/5. What else might be equivalent to 3/5? Well, I look on my multiplication table and I see that the row of 3 and the row of 5 are listed. I see also that 6/10, 9/15, 12/20, 15/25, 18/30, etc. are all equivalent to 3/5. How many fractions can we see that are equivalent to 3/5? I can count that there are 12 of them in this table. However, there are limitless. There is an infinite many that are equivalent to 3/5 if we were to continue our number chart and continue past the number 12. What number will make this equation true? 2/3 is how many twelfths? How many copies of 1/12? So I see on my number line, I have 2/3, but I want copies of 1/12. So therefore, I will cut my pieces into twelfths. So 4 from 0 to 1/3, 4 from 1/3 to 2/3, and 4 from 2/3 to 1. And then I can count how many copies of 1/12 it takes to arrive at 2/3. I see that there are 8 copies of 1/12 in order for me to reach 2/3. So 1, 2, 3, 4, 5, 6, 7, 8. What number will make this equation true? 4 copies of 1/12 is how many copies of 1/3? Instead, let's use a area diagram. So currently I have 4 1/12 shaded. I also see that this kind of separates naturally into thirds. The top, the middle, and the bottom layer represent thirds. And I see of the ones that are shaded, only one of the thirds is shaded. So therefore, 4 copies of 1/12 is the same as 1/3. The meaning of addition stays the same whether we are adding whole numbers or fractions. We can think of adding as putting numbers together to make a total. So let's use a number line to show the sum of 2 copies of 1/5 and 6 copies of 1/5 together is 8 copies of 1/5. I have my number line here and it's broken down into copies of 1/5. And we'll start with 2 copies of 1/5. So we start at 0 and I go to 2/5. Well, I need to count 6 copies of 1/5 more. So I need 1, 2, 3, 4, 5, 6 copies of 1/5 more. So altogether we arrive at 8 copies of 1/5. Use a number line to show the sum of 4/6 and 2/6. So I have a number line which is broken down into sixths. I first need to start with 4 copies of 1/6 and I need to go 2 copies more of 1/6. So I arrive at 6/6, which is the same as 1. Let's use an area model to show the sum of 7/12, 3/12, and 9/12. So I see I have an area model which is broken into 12 pieces. So I need 7 copies of 1/12 colored in, and I need 3 copies of 1/12 colored in as well. And further, I need 9/12 copied in, but I only have 2 left, which means that I need to bring in another set. So I have 1 full unit colored in, and I needed to bring in another one so that I could finish the remaining 7 copies of 1/12 being colored in. So if I were to add all the copies of 1/12, I see that there are 19 copies of 1/12 shaded in. So there are 19 twelfths. This is also the same as 1 whole unit plus 7 copies of 1/12 or 1 7/12. Just like whole numbers, fractions can be composed and decomposed, added and subtracted. Fractions and whole numbers follow the same thought process and are just more numbers on the number line. And I know I keep saying that, but if students are to understand that they're just like any other number, they're not to be afraid of them. So reiterating that is super important to me. Derek decides to start working on his sand designs. He has 4 1/3 cups of purple sand to use. First, he puts 1 1/3 cup of purple sand in one jar. How much purple sand does he have left? Next, he puts 1 2/3 cup of purple sand in a second jar. How much purple sand does he have left now? So we'll start on a number line. So on my number line, I have 1, 2, 3, and 4. And not only that, but they're split into copies of 1/3. So I start at 4 copies of 1/3. That's what we started with. First, he puts 1 1/3 cup of purple sand in a jar. How much does he have left now? So now we need to subtract 1 1/3. So I count over to the left, so subtract. I take away 1 copy of 1/3, which brings me here, and now I take away a whole unit, which brings me to 3. Further, so now he has 3 cups left. Next, he puts 1 2/3 cups of purple sand in a second jar. How much purple sand does he have left now? So we're starting at 3, and we need to take away 1 and 2 copies of 1/3. So if I were to go from 3 to 2, that would be 1, and I need to take away 2/3 cup more. So 1 2/3 cup more, leaving me at 1 and 1/3 cup. So we just did an example looking at what we call mixed numbers. I just want you to call them fractions because again, they're just like any other number on the number line. Let's decompose 2 and 1/4 to show that it must be the same as 9/4. In both of our fractions, notice that we have copies of 1/4 that we are looking at. So when I start at 2 and 1/4, I need to count over from 1, since it was blank over here. 1, 2, 3, 4 copies of 1/4, which would give me another whole. And then this other new one next to it, the other line would be 2 and 1/4. Let's see if we can show that that is the same as 9 copies of 1/4. So if I know from each distance is 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, 9/4. So 9/4 is 9 copies of 1/4. I hop over 9 times and sure enough, I land at the same location. Harry walked 1 5/6 miles to the beach, then another 5/6 of a mile to the store, and then 1 2/6 miles home. How many miles did Harry travel altogether? We know that to add them all together, we can decompose our numbers. So here we're adding all of our miles together so that we can show how many we did all together. And what I've done is taken my whole number pieces and rearranged them and separated them from the fractional pieces. I also know that 5/6 plus 1/6 would give me 6 out of 6, which is a whole. So what I did was decomposed 5 copies of 6, the second one here. I gave 1 copy of 1/6 here, and I broke this into 4 copies of 6 over here. So 5/6 plus 1/6 would give us 6 copies of 1/6, which we know is a whole, and 4 copies of 1/6 plus 2 copies of 1/6 is also 6 copies of 1/6, so another whole. Adding all of my whole pieces together, I see that Harry walked 4 miles. Fractions and decimals can be written in different forms. So let's start off by saying that we have 7 pennies. We know it takes 100 pennies to make a dollar. A dollar is the unit. We can say that 7 out of 100 is what represents the amount of pennies we have. When looking and using a hundredths chart or a flat, this also means that 7 out of 100 units are highlighted. We say this is 7 hundredths. Now let's say we have 3 nickels and 4 pennies. This is 19 cents or 19 out of 100, so 19 hundredths, and 19 of the 100 are shaded in our base 10 flat. This is written as 19 hundredths. Now we have 2 $1 bills, 3 nickels, and 4 pennies. In fractional form, this is 2 and 19 hundredths, meaning that 2 full base 10 pieces would need to be, for our unit, would need to be colored, and 19 more of a third one, so a portion. This is 2 and 19 hundredths. Now we have 3 quarters and a nickel. If we were to count, this would be 80 cents, so 80 hundredths. So 8 out of the 80 of the 100 units would be highlighted. Further, this is the same as 8 tenths, since 8 full ones are done. So we could also say that there are 8 out of the 10 highlighted. We can extend the idea of decimals using base 10 models with any decimal such as representing 1.42 meters. Represent 1.42 meters as a fraction and using base 10 models. As a fraction would be 1 and 42 hundredths. So one full base 10 block flat would need to be there, plus a portion of a second one, particularly 42 little units highlighted. Write 24 hundredths as a fraction and as a decimal. Use a place value chart to explain how they are connected. 24 hundredths is written as 24 over 100, meaning that there are 24 squares out of 100 colored in. When I look at my place value chart, 2 is in the tenths place and 4 is in the hundredths place, which is how we get 24 hundredths. The last number in the decimal indicates how we're going to say the decimal. Which letter best represents the location of 54 hundredths? Well, I can look at 5 tenths here, or 50 hundredths, and count 4 more, 1, 2, 3, 4. So it appears that C would be the best letter. What about 88 hundredths? So looking at my number line, I first want to tackle and say that this is 80 hundredths, or 8 tenths, and count over 8 hundredths more to get to letter E.